Okay, so welcome back to another video. So what we have here is a sum. So everything in the denominators consists of the fourth degree power, the reciprocals. So we have 1 divided by 3 to the power 4 plus 3 divided by 5 to the power 4 plus 6 divided by 7 to the power 4 plus 10 divided by 9 to the power 4, and it goes on, so on and so forth. So it might be a little confusing to see what pattern, or rather what generalization of a sum we have to really start out with. But if you notice closely that obviously we know that from the denominator we can actually guess easily that this is actually in terms of sums of the odd of the fourth degree power. But if you look at the numerator specifically, these are actually triangular numbers. So as we progress, each one is a triangular number progressing, so on and so forth. So at least we have an idea on what that sum is going to be and what we're dealing with. So beyond that, it's just a little bit, or not really a little bit, but it's mostly containing a bit of algebra manipulation and readjusting the index as well. And the important thing is that we actually have two special functions we'll be using, and that's actually going to help write things a little more better in terms of simplification, and the answer will come out nice just like it is. So with that, why don't we actually just jump right in? So as mentioned for our numerator, so let's first say that this is the infinite sum, and then this is actually our index will be n is equal to 1. The numerator, as we see, are actually just triangular numbers. So we have that this is actually written in the form of n times n plus 1 divided by 2. And then under the denominator we have is that this is going to be 2n plus 1 and then to the power 4. So what we can do obviously is that we'll just move that constant, the 2 outside, so 1/2, so it'll be 1/2, and then multiply our infinite sum at n is equal 1 of n times n plus 1, and then divided by 2n plus 1 to the power 4. So really that's our sum that we're actually going to be working around with. So notice that we can actually write our numerator a little bit differently. So I'll put the little star asterisk. N to the power, or n times n plus 1, can actually be written as the following. It can be written as the same thing as 4 times n squared plus 4 times n plus 1, and then subtract 1 divided by 4. And if you decompose this a more easier way, we have that this is the same thing written as 2n plus 1 to the power square subtract 1 divided by 4. And that's actually a good trick that we actually manipulate the algebra here, since this we have to utilize something in order to help cancel out the 2n plus 1 to the power 4 from that denominator. So in other words, so let's actually switch to a different marker to continue on with this. So in other words, what we have is that this is actually just going to be 1/2, and then now multiply, or rather now with the infinite sum, n is equal 1. And then so what we have here is that this is going to be, replace this, substitute, so 2n plus 1 to the power 4, then subtract 1, then divided by 4, and then of course our denominator is still 2n plus 1 to the power 4, which of course we just simplify things even further by factoring out the 1/4. So I have 1 divided by 8 of our infinite sum, n is equal 1. So that means this is actually just going to be, so 2n, so that actually has to be a square over here, my mistake. And plus 1 quantity square, subtract 1, and then all this being divided by 2n plus 1 to the power 4. And utilizing the nice property that we can actually use some linearity, that we can split this up into the difference of two sums. So for 1, I have it's 1 divided by 8, then multiply with our infinite sum, n is equal 1. So this is actually just going to cancel out the terms. So what we have is that this is 1 divided by 2n plus 1 quantity square, and then subtract 1 divided by 8. Then we have our infinite sum, n is equal 1 of 1 divided by 2n plus 1, and then to the power 4. So we have two sums that we're actually going to be dealing with. So the main issue arises is how do we compute such sums? It may look a little bit of a bit complex in a way. And you might be thinking that can't you just readjust the index? Well, that's not exactly the case. I actually did say that earlier, so my mistake for that. We're not actually going to be readjusting. Instead, we're actually going to take things to a little bit of a different approach. And it's actually more of an easier approach, because actually, first off, we're actually going to look at this infinite sum over here. Another way that it's actually standard to compute such sum is that you can actually apply the Fourier transformation specifically for the piecewise function of x and negative x. But here we're actually not going to do that. So what we'll notice is that specifically we know that Basel's problem, pi squared divided by 6, so this is actually where the two functions come in as I mentioned. pi squared divided by 6 is actually, so we know that in terms of that infinite sum expansion, that's going to be 1 divided by 1 squared plus 1 divided by 2 squared plus 1 divided by 3 squared, and then, you know, so on and so forth. So it's the sum of the reciprocals of the squares. So why don't we actually manipulate this a little bit differently? So let's multiply 1 divided by 4 into that entire expansion. So that means that would be pi squared divided by 24. In other words, that's the same thing written as pi squared. I'm going to keep this as 6, then multiply by 4. In other words, I'll write that in terms of the exponent of squares, so 2 to the power square. And then if we actually do this, this is the same thing written. So you just literally just multiply the 1 over 4 divided by to this entire expansion over here. That leaves us with 1 divided by 2 squared plus 1 divided by 4 squared, and then plus 1 divided by 6 squared, plus so on and so forth. So what that means is that this is actually, we're actually going to take the subtraction of the 2, so pi squared divided by 6 minus pi squared divided by 24. So what that yields us is that it's actually going to be pi squared divided by 8. And with that expansion, we know that we actually do the subtraction for these expansions of the sums over here. So we're actually just left with the odd reciprocals of the squares. So I have 1 divided by 1 square, and then add this with 1 divided by 3 square, and plus 1 divided by 5 square, plus so on and so forth, which we know that in terms of the series expansion, that's actually written as the same thing as the infinite sum starting with n is equal to 0 of 1 divided by 2n plus 1 quantity squared. Guess what? That's actually pretty similar to what we have over here, except that we have an n is equal to 1. Well, we just need to put in the n equals 0 term back into here and then take that subtraction. So that means, in other words, I'll just put this as a, you know, as a statement to sum it all up. So n is equals 0 of 1 divided by 2n plus 1 quantity square. That's the same thing written as 1 and then plus the infinite sum at n is equal 1 of the series that we're actually expanding out, 1 square, aka that's the same thing written as pi squared divided by 8, and then subtract 1. So with that, that's actually going to be our substitution back into over here. Okay, and so now let's actually do the same thing for our 1 divided by 2n plus 1 divided by 4, or to the power 4. So let me actually get rid of this. All right, moving on to now evaluating this series over here, 1 divided by 2n plus 1 to the power 4, starting with our index at n is equal to 1. So one thing we know is that specifically we're going to be using the Riemann zeta of 4, aka equal to pi to the power 4 divided by 90. I actually did a full derivation on that video. If you want to check out the proof to that, the link will be in the description below. It's actually utilizing the whole lattice multiplication tables, which I think it's a pretty interesting non-standard proof. The standard way to actually evaluate such function is you would have to apply the Fourier series. So with that out of the way, so we start with pi divided by, or pi to the power 4, and then divided by 90. That expansion written out we have is 1 divided by 1 to the power 4 plus 1 divided by 2 to the power 4 plus 1 divided by 3 to the power 4, and then continuing on, so on and so forth. So it's a reciprocal of the 4th degree of that expansion. So then let me continue just saying this is the Riemann zeta of 4 over here. Then let's actually fix the same, do a little bit of a similar argument that we just did earlier. So pi to the power 4 divided by 1040, which is the same thing written as pi to the power 4 divided by 90, multiplied by 2 to the power 4. So if you just do that same thing, see, it's actually a similar reasoning that we were doing previously for evaluating this sum over here. What we have is that the expansion is going to be written as 1 divided by 2 to the power 4. So you'll notice that what we're doing is that this is actually considering the even degrees or the even reciprocals of the term, and then we're actually going to subtract it. So that's the whole takeaway from here. So 4 to the power 4 plus 1 divided by 6 to the power 4, so on and so forth. So that means performing the subtraction then is meaning we're going to have, so pi to the power 4 divided by 90 minus pi to the power 4 divided by 1440. Then that yield us, so you do the simplification, do the butterfly math, and so on and so forth. It's pretty easy to see that we have 15 times pi to the power 4 multiplied by, so it's still 1440, but I'll decompose this to say as 16 multiplied by 90. And then what we have is going to be equal to 1 divided by 1 to the power 4 plus 1 divided by 3 to the power 4 plus 1 divided by 5 to the power 4, so on and so forth, which you'll notice that this is actually very similar to what we have over here. So putting that series or the summation, this is the same thing as n is equal to 0 to infinity, 1 divided by 2n plus 1 to the power 4. So just like before, we have a starting index as n is equal 1 and n is equal 0. So to readjust everything to get back into speed, what we have that originally, originally from starting from there, n is equals 0, of 1 divided by 2n plus 1 to the power 4 is the same thing as 1. If you evaluate this at n is equal to 0, then add this with our infinity, and then n is equal to 1. Of 1 divided by 2n plus 1 to the power 4. So in other words, that's the same thing written as 15 divided by 16. And I have a pi over 4 divided by 90. So I'll replace this with the Riemann zeta of 4 and then subtract 1. So with that out of the way, so that's actually our answer for this summation series over here. And so everything just comes in full circle. So now we just do the simplification. So now let me go back to the black marker just to finish everything off. So now we just perform the substitution. So 1 divided by 8 multiplied by pi squared divided by 8 minus 1. Then what is it? Subtract 1 divided by 8 multiplied by 15 over 16 multiply the Riemann zeta of 4 and then subtract 1. So simplify everything of all that out. So let's see, we have pi squared divided by 64, then minus 1 over 8. And then what we have is minus 1 over 8 multiplied by 15 divided by 16, then times the Riemann zeta of 4. I'm not going to go through that full expansion. Rather, let me actually replace the Riemann zeta of 4 with pi to the power 4 divided by 90. And then that's it. So minus and then minus, so plus 1 divided by 8. So we have the 1 over 8 that's going to cancel. So it just leaves us now with just pi squared divided by 64. And then if you actually just expand this multiplication out over here, so we have this is minus pi to the power 4 and then divided by 768. And you could simplify it even further to say that this is just equal to pi squared divided by 64, multiply with inside the quantity 1, subtract pi squared divided by 12. And with that, that is our final answer to our sum containing of the 4th degree reciprocal, and that the numerator is actually in sequence of the triangular numbers. So there you have it. We have our function, that's our special function value, the Riemann zeta 4, and well, Basil's problems as well, 2 for 1. So yeah, that's pretty cool if you ask me.